Hello, everyone. Today's teaching assistant is Molly. Say hello, Molly. Molly is my oldest cat and the fluffiest. Okay, today we're going to cover the last type of descriptive statistics, which is relative standing, and that includes percentiles and what are known as z-scores. In order to understand relative standing, we need to look at how scores are distributed. Now, in the perfect world, scores are normally distributed. So what that means is that we've got a bell curve, and half of our scores are perfectly distributed on one side, and half are perfectly distributed on the other, and symmetrical. So one side mirrors the other. You've got the most scores here at the top with significantly fewer on either end. And because this is theoretical distribution, these tails go off to infinity. They don't actually touch to the y-axis. They're always just above it. With the normal curve, so this normal distribution, what we see is that our average, median, and mode are all exactly the same, right? So the mode, which is the most frequently occurring score, that's going to be right there. So is our median, which is that half point, and the average. All of them are going to be the exact same number. The other thing that's true for a normal distribution is the fact that about 2/3 of our cases are going to be found within one standard deviation of the average. So that's what this Greek letter mu signifies. Mu signifies the mean, and sigma, this Greek letter here, signifies the standard deviation. So within one standard deviation, we've got about 2/3 of our scores, and within two standard deviations, we've got 95% of our scores, and within three, we've got almost every score possible, which is very, very few outliers outstanding. However, in the real world, we very rarely have this perfect normal distribution. Instead, what we've got is skewed distribution. So where a distribution sort of leans over to one side or the other. When you've got a positively skewed distribution, you've got a lot of scores here on the high end. So we saw this last week with our average Canadian household income, right? There's all those millionaires and billionaires who are impacting the average household income in Canada. On the other hand, when you've got a negatively skewed curve, you've got some extreme low scores that are causing your skew, whereas you've got relatively fewer high scores pulling it this way. Another way of looking at it is to consider what the mean, median, and mode are doing. So with a negatively skewed distribution, your mean is always going to be your smallest value. The median is going to be slightly larger, and then the mode is going to be highest. With a normal distribution, as I mentioned, they're all the same. With the positively skewed distribution, your mean is going to be higher than the median and the mode. And again, this is why the mean can be very problematic to report for information that's heavily skewed, right? It's not actually giving us the true picture. Things like the median and mode are more accurate in those situations. The other way that distributions can be skewed is based on whether they are flat or peaked. When a distribution is normally distributed, it's what's known as mesokurtic. That's what we want to see. However, sometimes it's rather peaked, in which case it's leptokurtic. If it's very flat, it's platykurtic. And the easiest way to remember that is platykurtic sounds kind of like platypus. So picture a platypus lying down, and that is your flat distribution. The other way that a distribution can vary, as we mentioned last week, is when it has more than one mode. The important thing to pay attention to when you have a distribution like this is that it could be an indicator that you're actually looking at two different groups of people. So for instance, let's look at this graph here of the annual salary of some employees at a company. So when we plot the annual salary for everyone, we can see that we've actually got two peaks happening. So we have one peak here at around the $35,000 to $40,000 range, and another peak here at $135,000 per year. So what this is showing us is that within this organization, we've got one population of lower income earners and the second population of high income earners. So that means that we shouldn't treat the entire population of workers within this company as one population. We should treat them as two separate groups and examine them separately, because what might be true for our lower income earners probably won't be true for our higher income earners. And by treating this as just one group instead of two separate groups, we will miss out on these important differences. So this is another example of confounding effects. Other ways to look at the relative standing of information in relation to the rest of the scores is by looking at the percentile rank or percentile. So this is where you might have heard it in relation to your standardized school scores, or if you have children, your pediatrician has definitely used something like, oh, your child is in the 70th percentile. What that means is that your child weighs more than 70% of other children of that age. So by saying 70 percentile, we're saying that 70% of scores are below the score where your child is at. Another comparison that we can do is the rate. So this is looking at the ratio between two related quantities. So for instance, we can look at heart rate, which are beats per minute, or the tax rate, unemployment rate. This is used to contextualize findings and make comparisons across populations really quickly. One other way that we can make comparisons across populations when they don't have the same unit of measurement is to transform them into standard scores, otherwise known as Z-scores or Z-scores if you're American. What this does is it converts the original score into a score that considers its standing in relation to the mean and standard deviation for everybody in that population. So every single score that one of your participants obtains can be transferred into a standard score so it can be compared to others on a different measure. So for instance, you might have measured your client on the Beck Depression inventory when they started seeing you and obtained a score from that, but when they were referred to you, they came with a CSD. Depression score. So in order to compare, has there been improvement or not, you can standardize these scores and compare them to see, even though they're two different depression inventories, whether there's been improvement or not. The thing about standard scores is that they have their own what's known as standard normal distribution. So with the bell curve, we learned that that center point is the mean, median, and mode. However, with the standard normal curve, where our standard scores are, the mean is 0. And we've got our 1, 2, and 3 representing our standard deviations. And again, we've got the same distribution of scores as within the normal bell curve. within 2 standard deviations, we're having 95% of our scores showing up. So the reason we use 0 now as our mean is because of how we are making these comparisons, right? We don't want to have any units within our scores that we're comparing because, as I mentioned, we're trying to use 2 different scales, and with the original units, they're incomparable. But as soon as you standardize the scores and make them unitless, now you can look at how each score deviates below or above its mean. And that's why we basically force them to have a mean of 0 and to see how far away they are from that mean, how many standard deviations they are. Let me show you what that looks like with a real world example. So again, in my work, I work with domestic violence and child protection. What we get is a lot of referrals from child protection or concerns from police services, and they use what's known as the Ontario Domestic Violence Risk Assessment, or ODERA, to assess risk of reoffense and severity of reoffense. And it's used by police departments here in Ontario every time they attend a domestic violence call. The range is from 0 to 13, and the score is categorized from low risk to very high risk. On the other hand, within Child Protection Services, we use what's known as the Child and Family Risk Assessment in order to determine risk of harm to children, which is from 0 to 9, where we categorize, again, low risk to high risk. So suppose the police referred to Child Protection Services a family where the father was arrested for domestic violence and apprehended for breach of parole. Their score indicates high risk, or score of 5, but when the CFRA is conducted, the score indicates a low risk, or a score of 3. What should the child protection worker do given these 2 very different scores? Well, if they calculated the standard scores, what they could do is find out the percentile for these particular situation in this family. So if we standardize the ODERA risk score, we use that formula that's provided here and in the textbook, and we know from the research literature that the ODERA has an average of 3.45 and standard deviation of 2, and we end up with this Z score here. To determine how this translates into percentiles, we use this, what's known as a standard normal table. And this tells us, based on a Z score, just what the percentile is and how many people fall below that score. So we're at 0.695. So we look here, 0.6, and then we scroll over to see the 0.95, so we end up here, 0.2549. So that means approximately 25% of people are between 0 and our risk score here, or as a percentile, we can add this other 0.5 to it. So 75%. Our family is at 75th percentile for risk. Using the same formula for the CFRA risk score, we get a value of Z is 0.548. When we look at that table, 0.548, it's approximately 0.2088, so about here, and that's, you can see, a bit lower. It's now 70th percentile. So there's very similar scores, despite the fact that one is saying it's a low-risk family and one is saying it's a high-risk family. We're just seeing that there's different rules about when to intervene in child protection services. in this case, has a much higher bar for when they're going to intervene compared to police services. So that's just one example of how standard scores can help us. So the other way that we use standard scores is also to calculate the effect size. And the effect size is a statistic that portrays the strength of association in a study, no matter what the outcome measure is or what the unit of measurement is. And again, because standard scores are unitless, so that allows us to compare between studies. And the way it does this is by looking at how many standardized deviations two groups are from each other. So suppose the orange bar is a control group and the purple line is a treatment group. In this first example, we've got a little effect size of 0.05, or I suppose a medium effect is what the guidelines say that we should call it. And we can see that they're half a standard deviation apart from each other. So we can see that wow, there's still quite a bit of overlap between the two groups and what their scores are going to be on whatever the intervention is meant to address. The purple group is doing slightly better. If we look at where there are 3 standard deviations apart from each other, we can see now that there's very little overlap between the orange and purple groups. So this intervention is absolutely fantastic. Very few people are still experiencing whatever symptom it is that we're trying to alleviate. You will almost never get an effect size like this in social work. More likely are small and weak effect sizes. But the important thing is, and we'll discuss this in a lot of detail over the next few weeks, is that the effect size is what's most important in determining the significance of your results. Just because you have statistically significant results doesn't mean they're actually meaningful unless you interpret this effect size and determine, hey, how much better are people actually doing? So in review over the past 2 weeks, we know that nominal and ordinal variables can be described with frequency distributions and modes. Meanwhile, interval and ratio variables can be described with modes, medians, means, range, and standard deviations. Interval and ratio variables can also be normally distributed, or their distributions can be skewed, which impacts how reliable things like medians and means are going to be. The standard normal distribution and z-scores can be used to compare the ranking of scores on different scales and to calculate effect sizes.